the floor is yours, Igor.
Yeah. No, because you... Ok. Bom dia a todos. Antes da gente começar, eu vou dizer que, especialmente hoje, essa apresentação vai ser feita em inglês, por escolha da palestrante. So, first of all, good morning to everyone. Thanks for the presence of all of you. So, we have the pleasure to receive here today Professor Marcela Peláez from Uruguay. She's a professor of the Faculty of Engineering at the University of the Republic of Uruguay. Marcela has a very close relationship, professional relationship with France. She has been many times in, for instance, Sorbonne University, École Polytechnique, and she has also a very close relationship with Brazil. She has been in Natal, most recently, also Rio de Janeiro at the State University of Rio de Janeiro, and also the Federal University of Rio Grande do Sul. Marcela Peláez is a specialist in techniques for computing correlation functions of QCD, especially in the infrared regime. And now, today, she will present, the presentation title is Correlation Functions in the Infrared Regime of QCD with a Gluon mass. So, Professor Marcela, please feel free, take your time to send your message, and thanks once again for accepting our invitation.
Okay, thank you. I first want to thank Antonio, Igor, and Rodrigo to inviting me to give this talk. It's very important for me to be in touch with the Brazilian community, so I'm very happy to be here online. And okay, so what I'm going to talk about is more or less the same talk that I gave in Natal 2 weeks ago, but I extended a little bit because I have more time now. I also apologize because I'm going to speak in English. I don't feel very comfortable speaking in Portuñol, so I choose English. And also I have to apologize in advance because I think I got a cold yesterday, so because here in the south it's still cold. So, okay, just that. So what I'm going to present is just like a summary of the result that we have obtained for correlation functions, especially in the infrared regime, using this Curci-Ferrari model, that is a model that includes a mass term for the gluons. So this work is in collaboration with Nahuel Barrios, that is a PhD student, Sean Gracie, Urco Reynosa, Julien Sarraud, Mathieu Tissier, and Nicolas Chevre. So first I'm going to give an introduction, especially for the students. I don't know, I'm not sure that there are many students, but I'm going to give this introduction, maybe for the recording. And then I'm going to present the results for propagators and vertices, first for Yang-Mills theory, and then including the dynamics of the quarks. I'm going to talk about I'm going to talk about the quark propagator. So as you all know, quantum chromodynamics is a microscopic theory that is going to describe the strong nuclear force. So this quantum chromodynamic is expressed in terms of the fundamental particles that are the quarks and gluons, that are particles that have another charge that is called the color charge, that can be red, green, or blue. So this theory has a symmetry that is the SU3 gauge group. So the Lagrangian is going to be invariant under the SU3 gauge theory. A very important and interesting thing for the infrared is that quarks and gluons are bound together to form hadrons, and they haven't been seen isolated in nature. So that is a property that is called confinement, and we would really like to know how it is, how it happens. So if we want to compute correlation functions, we can use the Feynman path integral. So the Feynman path integral consists in summing over all possible fields configuration with a Boltzmann weight with the action. But it's better, especially if we, at the end, we want to compare with lattice simulations, to go to the Euclidean space, because in the Euclidean space, this correlation functions is like a mechanical statistic correlation function. So in the Euclidean space, we have the QCD Lagrangian that is invariant and under the SUN gauge symmetry, with n representing the number of colors. And we know that we are going to have this symmetry. So if we do this transformation, the Lagrangian remains invariant. This allows to define what are called the gauge orbits, along which the Lagrangian is invariant. And also, so if we want to compute the correlation function, we need to sum over all possible field configurations. And sometimes we are going to sum a lot of time the same contributions. So this gives an indetermination of the kind infinity over infinity. And we know that in order to fix the gauge and in order to properly define the correlation functions, we need to just take into account one only representative of each gauge orbit. So that is what is usually done by Faddeev-Popov procedure, that is learned in the textbooks. So the price that we have to pay in order to do that is to change the action by adding a term for the gauge fixing condition. For example, for Landau gauge is this one. And also we need to include another term with extra fields that are the ghosts, that is this other term. So now this Lagrangian has already, the gauge fixer Lagrangian is the Faddeev-Popov Lagrangian. And if we compute with this Lagrangian, we find that the theory is asymptotically free, that is what we want for QCD. So in the ultraviolet, we can use perturbation theory because the coupling decreases, but the same calculations says that the coupling constant goes to infinity for a finite energy. So in what is called a Landau pole. So in the infrared, we cannot use perturbation theory with Faddeev-Popov Lagrangian. So there are some alternatives that we may use. For example, some semi-analytical strategies. For example, the one based on Dyson-Schwinger equations. There are some important groups in Brazil that do this, work with this Dyson-Schwinger equation. There are also the functional normalization group equations, and between others. And of course, there are lattice simulations. Lattice simulations do a great job in order to study the infrared of the correlation functions. And one observation from lattice simulations is that the coupling constant does not diverge, and in fact, it remains finite and not so large. So at the beginning, we ask ourselves why perturbation theory doesn't work at all in this regime. So maybe one possible explanation is because of the existence of Ribot copies, because in the picture that I showed you before, I draw something like the gauge orbit just intersecting only once the gauge condition, but the case in the infrared is that the gauge orbit intersects several times the gauge condition. These are called the Ribot copies, and as I said, what we would like is just to take into account only one Ribot copy when we fix the gauge. So there are some tries in order to do that. There are, for example, the ones based on Griebus-Banziger action and the refined Griebus-Banziger action that are really very interesting works trying to restrict the domain of integration to a region without Ribot copies. Okay, and another observation from lattice simulation is that the gluon propagator goes to a finite value in the infrared, so it behaves more like a massive propagator than a massless propagator. So gluons behave as if they were massive in the infrared. So to summarize, lattice simulations find that the coupling constant does not diverge. In fact, it is finite and with moderate values. They also find massive gluons in the infrared. So we would like to have a theory that could reproduce all these observations from lattice simulations. So we wonder what is the simplest Lagrangian that allows us to reproduce these lattice results. So we try to first see what happens if we just add a gluon mass term in the already gauge fixed Lagrangian. So this term, in a way, can be thought that as it is taking into account the presence of Riemann copies, and is going to be part of the correct gauge fixed Lagrangian after, if we could succeed in taking into account the effect of Riemann copies. Because we include this term that is important after fixing the gauge. So this Lagrangian has some properties that allows us to prove that it's renormalizable, and in particular, it has been proved that it's renormalizable in the 70s, because this is a particular case of what are called Curci-Ferrari Lagrangians, and this in the case of the Landau gauge. So what we want to see now, if we can reproduce lattice data using this Lagrangian. So we are going to compute the gluon propagator. We first did this calculation at one loop, and also for the ghost propagator. And the only two parameters that we have to fit are the coupling constant, for example, at 1 GeV, and the gluon mass term. I'm going to show you later, but with the propagators, we can compute the flow of the running coupling constant, and also the mass running. Then, some years later, we extend the calculation to a two-loop calculation. So we have now a lot of more diagrams. Just to clarify, now the Feynman rules are more or less the same as in QCD, but our propagator is still transverse because we are in Landau gauge, but with a mass. So we have a lot of more terms, but we succeed in doing this, the two-loop calculation for the propagators. Here is the calculation for the diagrams that contribute to the ghost propagator and also to the gluon propagator. And the strategy to deal with these huge integrals is that we can reduce them, the Feynman integrals, we can reduce them in what I call the master integrals, that are integrals without numerator and with simple exponents of the propagators. So they can be represented here. And an advantage is that we can compute numerically these integrals, only this set of integrals in 4 dimensions, for instance. So with propagators, we can compute the normalization group flow, the beta functions, and the anomalous dimension. And in particular, this gluon mass term allows us to choose an infrared safe scheme. That means a renormalization scheme that is that doesn't present a Landau pole, so it is infrared safe. And for this renormalization scheme, we choose the normalization factors, and then we compute the beta function and the anomalous dimensions. We did this for one loop results and also with two loop results. So in this scheme, the gluon propagator can be expressed in terms of the running of the coupling constant and the gluon mass, and also the Gauss propagator. And this is due to the fact, to this relation, that both the coupling constant, because of the Taylor normalization scheme, but also the renormalization for the gluon mass can be expressed in terms of the renormalization for the gluon propagator and for the Gauss propagator. So we compute the one loop and two loop, and we compare the results with lattice data. And we have found that the results are very good. They are improved with two loop correction. This is for the Gauss, and here we can see that the results are improved from one loop to two loops. But also the correction is not so large. That is what we expect when we do perturbation theory. And we interpret this due to the fact that the coupling constant in this, at least in Young-Mills theory, is not so large. So perturbation theory is justified in this case. We also compare with the lattice simulations for the coupling constant in the Taylor scheme, and we also see that results improve from one loop, that is the dot plot, to two loop results. So once we have fit our free parameters, that are the coupling constant at 1 GeV, for instance, and the gluon, also the gluon at the gluon mass at 1 GeV, we don't have any extra free parameter. So, for example, for the Gauss gluon vertex, we have computed this vertex at one loop for arbitrary dimension, number of color, and for arbitrary cinematical configuration. And we extend also the results to the two loop contribution, but only in the case with to the cinematical configuration when the gluon has a zero momentum. Because in that case, the level of difficulty is the same as for propagators. So the kind of strategy and tools that we have to use are the same as we did for propagators. So we compare the Gauss gluon vertex with the lattice data, and we've seen that results are very good. And also the error is less when we go from one loop to two loop in the gluon vanishing momentum configuration. Okay, so we decided to extend the calculations for this more complicated vertex, that is the 3 gluon vertex. So because this is a really non-trivial check of our theory, because the 3 gluon vertex has a lot of a richer tensorial structure. So we have a lot of scalar functions that we can compare with. So for the one loop calculation, we compute these 3 diagrams with the corresponding symmetries, and we have computed these diagrams for arbitrary cinematical configuration, dimension, and number of colors, and we have compared also with lattice simulations. But then this is a recent work. We have extended the calculation to 2 loops, also in the case of one gluon vanishing momentum. So we have a lot of more diagrams to compute. This was part of the work of Nahuel's PhD thesis. So now we can compute the 2 loop and with the 1 loop correction for the 3 gluon vertex, also with lattice data, and we have seen that we obtain very good results. In particular, we can observe that for the one loop calculation, the zero crossing in our case, happens not so deep in the infrared, but when we go to two loops, the zero crossing goes deeper in the infrared, and that is compatible with what is observed by lattice simulations in 4 dimensions. Okay, so we think that we have very good results at one loop, and also the two-loop corrections shows that perturbation theory in young Mills theory works really well when we use a gluon mass term in order to reproduce the infrared behavior of correlation functions. But what about the quark sector? So if we want to compute...
Marcela?
Yes.
So it's Antonio, sorry. Can I ask you a question before you introduce quarks?
Yes, of course.
Okay, thanks. So you have provided several, amazing results in terms of even quantitative precision for correlation functions when compared with lattice data. But I'm just wondering, have you tried to compute, for instance, glue spectra within this model? Because I think that would be, let's say, really nice, because you have quantitative, let's say, precision in terms of correlation functions. And I guess that computing correlation functions of f mu squared, and things like that would be really nice.
Yes, we are on it. We haven't finished yet. No, in fact, we recently started that calculation or thinking about that. But I think it's the next step to do that.
Okay, thank you.
So, okay, now I'm going to the quark sector. So the first quantity that we want to compute is the quark propagator. For the quark propagator, we have two scalar functions. The first one, we're going to call it the dressing function of the quark propagator, and also we have the quark mass. So we have computed at one loop, and we can see that the quark mass is, okay, more or less fine, but the Z function is horrible reproduce. So one possible explanation for this is that this dressing function for the quark propagator has very important two-loop contributions. And this is still in QCD without a gluon mass term, because just in QCD without the mass for the gluon, this quantity, the more important contribution for these quantities are two loops result, because for the one loop result is vanished just for, I think, for coincidence in Landau gauge. So it's really important to go to see what happens at two loops. So we have extended the results to the two-loop contribution, and we can see, especially, I'm going to focus on that scalar function, that the results are very good and they change a lot from one loop to two loop. And we think that the reason is that in this particular case, two loop corrections are very important for this quantity. And I can also show you, I'm also showing you here the contribution for the gluon propagator that we have seen that is very good when we go from one loop to two loop, but also for the quark mass, we obtain better results if we go from one loop to two loop. But still, in the quark sector, there is a problem, that is that if we want to study the quark mass for really in the chiral limit, we are not going to succeed to prove that property, because if you do perturbation theory, you cannot, at a finite order, you cannot reproduce the spontaneous chiral symmetry breaking. So even though the results are better, we would like to have that property in order, to, for example, to study more hadron properties or something like that. So we understand that the huge difference between the the Gauss-Gluon sector and the quark sector is that the strength of the vertices from the Gauss-Gluon vertex to the quark-Gluon vertex is different, and they are related by a factor that depends on the cinematical configuration, but it's around 2 or 3. So the coupling constant, that means that we are, of course, in the Lagrangian, we have only one coupling constant, that is the Baire coupling constant, but we are going to renormalize them differently in the infrared, the one that is associated to the Gauss-Gluon vertex and the one that is associated to the quark-Gluon vertex. So we are going to introduce 2 different renormalization factors and see what happens. In particular, because we see that these vertices behave differently in the infrared. So we propose to study the theory taking the Young-Mills coupling constant on one footing, and the other one, the quark-Gluon coupling constant, in a different way. In particularly, we have seen with this one loop and 2 loop results that the Young-Mills sector can be treated perturbatively, but that is not the case for the quark sector. So we are going to do that just to consider that the coupling constant, the Young-Mills coupling constant, is small in the infrared, and we are going to treat it as a small parameter, but we are not going to do that for the quark-Gluon coupling constant. In addition to this, we are going to study first the Larsen-C limit. So in this Larsen-C limit, the gluon propagator can be replaced as a double color line. And this allows us to do the tooth limit and count which are the diagrams that contribute the most in this limit. For example, the coupling constant in this limit behaves as 1 over the square root of the number of colors. But if we have a loop of color here, we are going to have an extra NC factor. So for example, this diagram is of order 1, because we have 2 coupling constant and 1 extra color factor from this loop. In the first case, we don't have a loop of color, so we only have the 2 coupling constant. So this diagram is suppressed in the Larsen-C limit. So the expansion that we want to suggest is using 2 small parameters. The first one is the Young-Mills coupling constant, and the other one is 1 over the number of colors. So the idea, this is a way to order the contribution of the diagrams. So the way that we are going to implement this is that if we want to study the L order of this expansion, that we're going to call it the improved expansion. So in order to study this order, we are going to take all the diagrams, the normal diagrams, until the same order. And we are going to count the powers of the Young-Mills coupling constant that they have, and also the contributions in the number of colors. And we are going to add all possible higher loop diagrams that have the same number of the coupling constant and 1 over NC powers. So in following that rules, I'm going to show you the example that is to study this rainbow improved expansion at the leading order. So we are going to take into account only the situation where we don't have the Young-Mills coupling constant and neither suppressions in the Larsen-C limit. So for example, for the gluon propagator, at one loop, it's at 3 level, because we are going to study the leading order. So we see which are the exponent in the coupling constant, and also in in the NC limit, which is the behavior of the tree-level contribution, and we study if the higher loop diagrams can give the same contribution. And in the case of the gluon propagator, we can see that no higher loop diagrams have the same contribution as the tree-level propagator, because these ones they can be neglected because they have a Young-Mills coupling constant, and the other one because it is suppressed in the large NC limit. So in the leading order of this double expansion, the gluon propagator is just the tree-level propagator. The same happens in the quark-gluon vertex. So for the quark-gluon vertex, we have at the leading order is the tree-gluon vertex, and we are going to study the one loop diagrams. So the first one has a Young-Mills coupling constant, so we can so it doesn't contribute at this order, and the other one is also suppressed in the large NC limit. So for the vertex, we have the same situation. The only contribution is the tree-level contribution, because we are just studying the zero order of this analysis. What happened for the quark propagator? So for the quark propagator, we have the tree-level quark propagator, and we want to study if there are more diagrams that have the same behavior as this propagator. And we can see that, of course, we have to neglect all the diagrams that have a Young-Mills coupling constant. So these are the red dots. Then we are going to suppress the ones that are suppressed by the large NC limit. However, there are still some diagrams that are not suppressed neither for the Young-Mills coupling constant or the large NC limit. And in particular, those diagrams are the ones that are called the rainbow diagrams. So in the case of the gluon propagator, there are other diagrams that survives, not only the tree-level diagram. We have all the rainbow diagrams. And in particular, this can be resummed, and we can obtain what is called the rainbow approximation. And this rainbow approximation for the quark propagator has been extensively studied, and we know that from the literature that it can reproduce the spontaneous chiral symmetry breaking, and it was generally used without completely understanding why we can neglect some diagrams and not others. And we think that in this way we can understand why we can obtain this rainbow approximation in order to study the quark propagator. So we have studied this result, this rainbow approximation, in the case with a gluon mass term. We find the massive solution and the chiral solution in the ultraviolet. And we have solved the system in order to have the results and compare them with the lattice simulations. And we choose the most chiral results that we had that there are in the literature for the quark mass, and we compare it with our result for the rainbow equation, and we obtain very good results. Much better than doing a one loop or two loop approximation. Okay, just to conclude, first to summarize, we work in this Curci-Ferrari model in Landau gauge. That is a model that includes a gluon mass term. We think this gluon mass term as arriving an emergent phenomena from taking into account Gribov copies. This gluon mass term regularizes the infrared, so there are a lot of calculations that we can do, and in particularly, it allows us to define an infrared safe scheme. That means a normalization scheme without a Landau pole That is what is observed by lattice simulations. And if we do perturbation theory at 1 loop and 2 loop in Yang-Mill theory, we find very good results. However, the quark sector is more complicated. And even though the situation is better from 1 loop to 2 loop, it's not enough, for example, to reproduce the spontaneous chiral symmetry breaking. However, the fact that the Yang-Mill sector can be treated perturbatively allows us to understand better how we can treat the quark, for example, the quark sector, and in particularly allows us to understand how to arrive to this rainbow approximation that in fact reproduces the rainbow equation and the spontaneous chiral symmetry breaking. Okay, thank you.
Well, thank you so much, Marcela, for your presentation. And before we start the question section, let's open our microphones to thank the presentation. Please, let's go. So for the questions, please feel free to open the microphone and make the question. Teresa, please, go ahead.
It's not really a question, it's more like a comment and a compliment. Just very glad to see the results collected here, and I've been very enthusiastic of Marcela's work. I was in her thesis, I think, maybe, 7 years ago, I don't know. And I just think it's very interesting because we keep saying it's non-perturbative, but if you do it in a certain way, it is perturbative. If you do it, I guess, in a smart way. And so I'm very glad. And I was thinking, maybe this is not so relevant, but since we talk to people who use perturbative techniques, we have recently done a study with Diogo Boito from our department, who does perturbative QCD, and they used the PADE analysis, and we did this discuss together of our very old gluon propagator and ghost propagator results. And maybe this is something that will be of use, I don't know, because for them, it was an important thing because you use the PADE approximates for a fit, like we've done fit of our data before, even with the people from Ghent. But the way they do it, they have a much better control of the Taylor coefficients of the propagators. So maybe that's interesting in some way to compare to some perturbative series. It was, I think it was uploaded today to the archive, so it should be somewhere. But again, very nice, and yeah, congratulations, very nice.
Thank you, Teresa.
Thank you so much, Teresa, for your comment and compliments, and thank you, Marcela. So, anyone else, feel free to open the microphone.
I do have a question. It might be quite stupid, but let me ask you anyways. So you said that when you fit pure Yang-Mills results with lattice data, you just have the coupling constant and the mass to adjust.
Yes.
Right? So when you introduce quarks and you do the fitting, I mean, do you use how does the fitting compares with the gluonic sector, in the sense that do you use the values of the mass and the coupling constant from the gluon sector to the quark sector?
Yes, okay. In the case, because I present a mix of the two works, if we talk about only the perturbative calculations from the 1 loop and the 2 loop calculation for the quark propagator, for instance, we only have one coupling constant and the gluon mass. So in order to, we choose those parameters in order to reproduce at the same time the gluon propagator, the ghost propagator, and the quark propagator. So we do like
some sort of
error
optimization.
cloud.
Yeah.
Yes.
Okay.
So we
Okay.
choose the best parameter that in a way try to fit better all the propagators at the same time.
I see. And my second question is more of a conceptual nature. I mean, of course, I completely understand that this is an effective model that does a great job with within perturbation theory. But of course, in the end, I mean, one wants to assign some meaning or some interpretation for this mass of the gluon. So what is the view of the Curci-Ferrari collaboration on that?
Okay, we think that if we could properly take into account this effect of the Reebok copies, we are going to have a term that behaves as a gluon mass term. But we tried, we did several efforts in order to answer this question, but we don't have a completely satisfying answer for it. There is a work by Mathieu and Julien. They sum all the Reebok copies with a Gaussian weight, and they obtain like a gluon mass term. But it's not because they have this, they do this replica trick, and they have to at the end take the n number to 0, so it's not well defined, but it's okay. Still, it's like a hope that to see that this gluon mass term could arrive from there.
Because well, let me extend a little bit.
Yeah.
Because of course, because as you said, I mean, you introduced the mass term, and the way that is introduced, it's not BRST exact term. So it is, I mean, for sure, it will enter physical correlators, right? So it could enter F mu squared correlators. So it has some physical meaning, I would say. And just perhaps and then there's a comment, which is, so I, together with, I think in this room, it's just Giovanni, we asked the question whether this massive model would work in a completely different gauge. For instance, if you compute correlation functions in the maximal abelian gauge, which is a completely different gauge. And it turns out that if you do the one loop calculation for the gluon propagator in the maximal abelian gauge, the results are quite promising as well. So it's just a naive massive extension of the maximal abelian gauge.
So great. We have tried other gauges that are this with this chi parameter. And we have compared with with the lattice simulation, and they give also very good result. But I haven't seen the result for that gauge that we are talking about.
Yeah, it's not published. I mean, we are writing up.
Okay.
But then, I mean, when you introduce a mass gauge parameter, as you said, and then I'm afraid that this model will bring in several issues with gauge parameter dependence, I guess.
Yeah.
Okay.
I have the. Okay, yes, that is something that we have to investigate, because that is related with the fact that we don't know completely the origin of this gluon mass. So.
Yeah. Okay, thanks a lot.
Thank you.
Thank you so much, Antonio, for questions and comments. Thanks also, Marcela, for the answers and comments. Anyone else, please? So if we don't have any questions, let's open again our microphone, and thanks again the presentation. Marcela, thanks so much.
Thank you.
Marcela, finally, thanks once again for accepting contributing with us. Okay, and feel free to always attend the seminars.
Yeah, thank you.
Okay.
I'm going to do that.
Okay.
Thank you
Well,
very much, Marcela. Nice to meet you.
Okay. Bye. Thank
Bye-bye.
you.
Tchau, tchau,
Bye.
Tereza. Tchau, tchau.
Ciao.
Tchau, tchau.
Rodrigo,
Prazer.
acho que você pode parar a gravação, Rodrigo.
Tchau, tchau.
So great talk, Marcel.